class, we are on chapter 9.6. This is quantum mechanical orbitals and electron configuration. So we're going to look at principal quantum numbers and orbitals. The easiest way to understand this is how we identify an electron is through its electron configuration. An atom is through its electron configuration. Simple way to describe it is an address. We all have an address to where we live, and that's how we can locate your house on a certain street, is because there's an address, and that number pertains only to the property that you live on. And that's the same thing that we're going to look at. It's a little bit more complicated than that, but that's exactly the big premise of this. Is it's got fancy names, but it's an address to determine where these electrons are located on, in the sense of this property. So there's going to be values given to it. So we start so if you look at this bookshelf, if we had to load electrons on, similar, think of them as books, we would start at the bottom shelf. Normally, I would be lazy. I would just put them wherever they're on eye level for me. But there's a certain way that we have to load electrons onto an atom. And we start at the bottom. So we start at n equals 1. And then when that's filled, because there's only so many books that are allowed on that shelf, then we have to load onto the next shelf, and on the next shelf, and the next shelf. So if you see there's an arrow here, and the arrow goes up. So anything that's on N1 is lower in energy. N2 has higher energy than N1, and 3 is higher energy than N2, and so forth. So if you start closest to the nucleus, that's considered the lowest energy. And as you go out, it's considered higher energy. So the lowest energy orbital is called 1s. So it's a 1, and we call it s. We're going to get more into it. But this level right here, so this whole shelf here is called a principal quantum number, and it specifies the principal shell of the orbital. So what this means is that, let's say that this is your address. This principal quantum number is your address. But then we're going to look at the bedrooms inside the house, and they're also going to be denoted with a certain letter. That means that, let's say S is the bedroom, and P is the master bedroom, and so forth, is D is the kitchen. So we make these letters be the bedrooms. So the principal quantum number is your address. That is where we can find, and I'm really oversimplifying this, but I'm trying to make a way to understand this, is that's where you live. Then we expand into where you live, and we put letters to each room. And if I wanted to say, well, this person's in this room, then I could say, oh, they're in 1S. Okay, so you're on the first level, and you're in one of the bedrooms that's labeled S. That's where I can find you. So that's what this means. So principal quantum number is just the shelf itself. So this is n equals 1. So this is principal quantum number 1. This is principal quantum number 2. And let's say that these books are the bedrooms on this shelf. And you can see they're different colors because they're different rooms. These are not all the same books, so we can't treat them the same. And then n equals 3, and so forth. Okay, so the single electron of an undisturbed hydrogen atom at room temperature is a 1s. Hydrogen has 1 electron. It doesn't have more than 1 electron, so it can only fill in 1 orbital. And that is the lowest orbital in all of this is 1s. So it will take up, an electron will take up the 1s orbital. This is called the ground state. So when electrons are in their ground state, they are in their lowest energy, and that means they are not excited. They are just there hanging out. The absorption of energy by a hydrogen atom can cause the electron to jump or make a transition. This is when it will jump to another level. Depending on how much energy it has, and if it can go into that level, it will jump into that level. And that's what you're seeing here, is that it will go up, but that same value will also eventually have to leave that electron to let it go right back down to its own state, its ground state. So when we talk about ground state, we mean electrons that are not excited, they're in their lowest energy level. So in this case, we can see that to make a transition, the 1s orbital to a higher energy, when the electron is on higher energy, it is called an excited state. So when we say ground state, we mean lowest energy, nothing exciting going on, they're just hanging out. But when we talk excited state, that means they are excited. They bumped up. They're running up another level. Think of parkour, whatever helps you understand that it's being moved up into another level, excited, but eventually got to come back down to where it was at. So all the atoms of each element have one ground state and many excited states. That just means that in excited states, that an electron can go up to different levels. And if a hydrogen, so when we talk about hydrogen, we're not talking about one hydrogen atom. If you talk about hydrogen gas, we've got many hydrogen atoms in there, and all of them can take in different energies. So one might jump to n equals 2, but another hydrogen electron might jump all the way to n equals 5. That's what you would see, a different color, and so forth. So we're talking about a bunch of different hydrogen atoms, but they're all excited to different energy levels. So energy increases with a quantum number. So that's a main word you should know. Principal quantum number or quantum number, depending on where you read this. The higher the quantum number, the higher the energy. The lower the quantum number, the lower the energy. So the principal quantum numbers are n equals 1, 2, 3, and so forth. Since 1s has the lowest possible energy, that tells you that it's in its lowest energy shell and the lowest possible energy. So n equals 1 means it's like a bookshelf. It's on the first bookshelf, and it can only be in one book on that bookshelf, and it cannot go anywhere else. So S is the lowest energy level, lowest shell. We're going to look at different shells, and what we mean as shells are orbitals, and that's considered like bedrooms if you think in a house. And let's say, or an apartment building in a sense, one apartment is only on the ground floor, and that's the only place that this one electron can live. Can't go anywhere else. So shapes of quantum mechanical orbitals. So the letter indicates the subshell of the orbital. So this is very similar to a bookshelf, and we have different books, and each book is handled differently. So one book is nicer than the other, one's more expensive, and one's something nobody likes in a sense. So they're all given possible letters, and that tells you where that electron is. So this is like an address. You live in your house. You have your quantum number, but now the S, P, D, and F are which bedroom you sleep in. So that's where we're now expanding even more into thinking of looking in levels. So orbitals within the S subshell have a spherical shape. So all these letters that we see, these are called subshells, and they all have a specific shape to them. So S's are the easiest. They're lowest energy. They are spherical. They're like a ball. Orbitals are sometimes represented by dots, and the dot density is proportional to probability. So remember, now we say that we can, by probability, determine where this electron may be because of statistically of experiments, but we will never know exactly where it is, but this is the highest probability it'll be. So we represent it with the dots. So the dot density for 1s orbital is greatest near the nucleus, and it decreases further away from the nucleus. So you see how it starts spreading out? That's because the electron's more likely to be found closest to the nucleus than farther away based on the experiments that have been done. So subshells. Now this gets a little complicated. Principal quantum number is like a bookshelf. Subshells are the books on that shelf, and they're all different, and they all have different energy. S has the lowest energy. The highest energy is F. If an arrangement of electrons that determines the physical and chemical properties of an element. So think of the subshells as bedrooms. If you have siblings and you want the nicest bedroom, that would be maybe the highest energy. The lowest energy might go to, whichever sibling, I don't know, however people decide how bedrooms go. But, the nicest bedroom usually might go to the oldest because he had first dibs, or he or she had first dibs on it. And then it goes, and then as that person moves out, then the next sibling will take the nicest bedroom and so forth. So that's how you can kind of look at this. Each energy level consists of one or more subshells. The number of sublevels in energy level is equal to the principal quantum number n of that energy level. So n equals 2. So there's 2 sublevels. That's what that fancy sentence means, is that the principal quantum number, if it's n, it only has one subshell. If it's n equals 2, there are 2 subshells on that. So 2 books, where n equals 1 has 1 book. N equals 3 has 3 books, so 3 subshells. N equals 4 has 4 subshells, 4 books. The sublevels are identified as S, P, D, and F. Now here's the thing, that S, P, D, and F is for every level. So 1 has 1 level, so it has the lowest, starts with S. 2 has 2 levels, so it's 2s. So it starts expanding out, but that's the order it is. 3 has S, P, and D, and 4 has S, P, D, F. So it starts expanding out the more the energy. So it's lowest energy to highest energy. And I got a couple of these just to show you they're the same thing. The number of subshells in a given principal number. So it's exactly what I said. If you take the quantum number, that's how many subshells it is. So n equals 1, 1s. N equals 2, s and p. It goes in the order of what you see here. 3, SPD, 4, SPDF. Same thing here. Now, we call this subshells. This called sublevels. They mean the same thing. I put them both up because books don't keep the terminology consistent at times. So sublevels, subshells, same thing. And this just shows you it's broken up a little bit more. Okay, so orbitals can be represented as geometric shapes that encompass most of the volume where electron is likely found. Right now, we just showed you 1s, which is a sphere. But I'm going to show you the other ones, and they get more complicated. The 1s orbital is represented as a sphere and encompasses the volume within the electron is found 90% of the time. So remember, we have the probability, the likely probability that's where the electron is, and that's where we'll believe it to be, and not outward from that a bunch of dots. So if we superimpose the dot representation of a 1s orbital on the shape representation, we can see that most of the dots are within a sphere, meaning that the electron is most likely to be found within that sphere of the 1s. So basically, if we put a circle here and we put this dot, this is somewhere in here is where this electron exists. That's the highest probability based on experiments, and not somewhere out here, further out. Okay, so representation of orbitals. Dot density is exactly what it means. It's dot. But if we do it as a sphere, that still means that the electron is somewhere in this sphere. And both represent, so we superimpose them, nothing really changes. It's exactly matching the same thing. So one's just dot, one's shape, and then both superimpose. The greater the dot density near the middle represents a higher probability of finding the electron near the nucleus. Okay, so the s orbitals. Now remember I told you that n equals 1, the principal quantum number, has one orbital. 2 has an s and a p. So even though there's a 1s, there's also a 2s. And then if you go to 3, there's a 3s and a 4s. So every level starts with an s orbital and it expands out. But the difference is you start with a 1s that's small. So I don't know what those little dolls are that you pull them apart and there's another doll in it, and then you pull it apart and there's another doll in it. This is an example of that. I don't know what they're called, even though I have one. Yeah, I have one of those. I bought it in Europe. This is exactly that. The 1s can fit in the 2s, the 2s can fit in the 3s. So it gets bigger with the higher energy that we go. They all fit within each other. So the location, so each sublevel has one orbital and can hold a maximum of 2 electrons. So what I haven't talked about yet is that this sphere here can hold 2 electrons. So somewhere in here is 2 electrons. Somewhere in here can hold 2 electrons, and something in here can hold 2 electrons. Even though they get bigger, they can only all hold 2 electrons. That rule never changes. Only 2 electrons if it can hold 2 electrons. The location of an electron is described in terms of probability. Orbitals are 3-dimensional volume, which electrons, so that's where you see the x, y, and z here. It's supposed to be 3-dimensional, where the highest probability of the electrons to be found. S orbitals are always spheres. The electron cloud of s orbital represents the highest probability. I've already said that. The s orbitals are shown as spheres, and the size increases because they contain electrons at higher energy levels. So they're bigger because as you go up, remember the energy, we go all the way to the beginning. Well, I guess we can use this one, but I like this one. As you go up, the energy level increases. So the level is bigger because those energy levels, it has more energy on those levels. Okay, but if you think about it, this can fit in this can fit in this. The 2s orbital is similar to the 1s orbital and larger. The 2s orbital is similar to the 3s, but the 3s is larger. That's only the point that we're trying to make here. But they're all different levels. The 2p orbitals, so now we're going to look at p's. So if we go back, remember these energy levels, these are our subshells or sublevels. Every level matches its principal quantum number. So at 2, we now see 2p orbitals, but they're also in 3p, and they're also in 4d. So we have p orbitals here, we have d orbitals here, and we have f orbitals, but all of them have s orbitals. So if we look at p orbitals, they look very different. S's are the easiest. These look like, I don't know what you would call these. Anyways, they look like they're kind of like a balloon that's twisted in the middle, and it's going in opposite directions. So this shows a dot representation, and there's 3 p orbitals in every level. So that's why you see 3, 3, and 3. Now what they represent is one orbital is on the x-axis, one is on the y-axis, and one is on the z-axis. So that's where the px, py, and pz come from. One is on the, so that's what those 3 blocks, that's what they represent. The px, the py, and the pz. They're all in shapes, and they're all facing a different axis. But there's a dot representation, and usually we draw them like this, which mean the same thing if you overlap them. P orbitals, there are 3 p orbitals starting with n equals 2. Each p orbital has 2 lobes. There we go. Lobes. I forgot all about this. Like a balloon tied in the middle. That's where I got that from. And can hold a maximum of 2 electrons. So just like the sphere, regardless of size and energy level, there's a trend. All of these subshells can only hold 2 electrons, and that is it. Think of a bookshelf that can only hold 2 books, and you have to move to the next bookshelf. It will never go past that. So, for instance, you have 3 subshells in one level. That means that this can hold 2 orbitals, 2 electrons, this can hold 2 electrons, and this can hold 2 electrons. So that means that there's a maximum of 6 electrons that can be held in these orbitals. So that's like a bedroom, which can only sleep 2 people, and that's it. So each p sublevel has 3 orbitals. So when you think of a sublevel or a subshell, there are 3, and there's always 3, but they can hold a maximum of 6 electrons and only 2 within each lobe, which in each subshell itself. So a p orbital has 2 regions of high probability. It gives a dumbbell shape, and it's lined along each axis. Okay, so the next principal quantum level is 3, and that means that it has 3 subshells, S, P, and D. The S and P subshells contain the 3s, and the 3 p orbitals similar to shape to the 2s, and 2 p orbitals are larger and higher in energy. So basically they get larger as they go up the level, but they still can only hold 2 electrons in each orbital. The D subshell contains 5. So if we look back to here, this is one subshell. P's we just covered has 3 different, so px, py, and pz. The D has 5 different orbitals in it, 5 different subshells, and F has 7, which we're really not going to cover F. But D are all over the place. They look very different from each other. So each one of these can hold only 2 electrons. Even though they're funky looking and they look bigger, still can only hold 2 electrons. So I found a nice little gift that matches this one here that looks like a baby rattle in a sense. Still only 2 electrons. That's why it can only hold a maximum of 10. 2, 4, 6, 8, 10. That's it. No matter how elaborate they look, still only 2. So basically, overall, the rule is for each orbital can only hold 2 electrons, and then you have to move on. You have to go on to the next whatever's available. So the D sublevels contain 5 orbitals, and they look pretty weird. And they have, this is on the Y and X axis. This is the Y and the Z axis. This is the X and Z axis. And then it gets into even funkier names, if that's what you want to call them. So 4 of the 5 d orbitals consist of 4 lobes and are aligned longer between the different axes. Pretty much, they look like they're in between. 1 d orbital consists of 2 lobes, and a donut-shaped ring, I can't speak, around its center. So if we go back here, the trend is all of these can only hold 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So n equals 4 can only hold 32 electrons. N equals 1 can only hold 2 electrons. N equals 2 can hold 2, 4, 6, 8 electrons, and so forth. So hopefully you're getting the idea that regardless of what subshell, what level, it can only hold 2 electrons. All right, so here's just another representation with a dot representation of what this looked like based on experiments. And then I found a nice gift that had them all on here, which is pretty interesting. Okay, so there's a maximum number of electrons, which I kind of went over already. Each s sublevel has 1 orbital and can hold 2 electrons. Each p sublevel, which has 3 orbitals, those lobes, has can hold a max of 6 electrons and 2 in each orbital. Each d sublevel has 5 orbitals and in total can hold a max of 10 orbitals. And each F sublevel has 7 orbitals and can hold a total of max 14 electrons over those 7 orbitals. So the quantum mechanical model predicts the bright line spectrum of hydrogen as well as the Bohr model. The quantum mechanical model can predict the bright line spectra of other elements. So Bohr could only predict hydrogen, and the quantum mechanic model could predict and give accurate information about other elements. The Bohr could not do that, just with electron. So the Bohr model was replaced with this model, this quantum mechanical or wave mechanical model. The Bohr model still is important because this is where we got our foundational understanding of this. So that's why it's always taught, but then we expand on the quantum mechanical model. That's it.